All right, so let's use these impulse graphs along with what we've already found with change of momentum in order to determine some factors that we want to be able to find. All right, so on page 233, number 3 in your book, it says a 7.0 kilogram bowling ball is rolling down the alley with a velocity of 2.0 meters per second. For each impulse A and B, so that's these two down here, A right there, B right there. For each impulse, as shown in figure 9-3 below, find the resulting speed and direction of the motion of the bowling ball. All right, so first and foremost, we need to find the impulse of both of these. This one has a base of 1 and a height of 5. This one has a base of 1 and a height of -5. So we're going to get +5 for A for that impulse, and then -5 for the impulse on B. All right, so we're going to go ahead and do this problem. We're going to do part A first and then do part B. Something to note here is that positive is going to be toward the pins and negative is going to be away from the pins. So in part A, we have an impulse of positive 5.0 newton seconds. We have the mass and we have the initial velocity. We need to find the final velocity, so we're using the equation impulse equals change in momentum. Go ahead and plug in our numbers. We get an impulse is 5 newton seconds. That's going to be equal to 7 times final velocity minus 7 times 2. That gives us 14. So we get 5 equals 7 times final velocity minus 14. We'll add 14 to both sides. That's going to cancel the 14 from the right side, and then we'll divide by 7, and that's going to cancel the 7 from the right side and leave us with a final velocity of 2.71 meters per second. Now, because this is positive, that means it's going to be toward the pins. Now, something interesting here is you notice that it's going to be faster than the initial velocity. Well, if impulse is net force times time, so if the impulse is positive, then that means the net force is going to be positive. And by Newton's second law, if we have a positive net force, that's going to mean we're going to have a positive acceleration. So with a positive acceleration and a positive initial velocity, that means the object should speed up. So we get a velocity that's greater than the initial velocity because it did speed up. In part B, we have a negative impulse, which is negative 5.0 newton seconds. We'll go ahead and plug that in our equation. We get impulse is going to be equal to change in momentum. So we get negative 5 is going to be equal to 7 times final velocity minus 7 times 2. Again, that's going to be 14. We add that 14 to both sides. That cancels the 14 from the right side. And then we divide by 7. And that gives us the final velocity is going to be 1.29 meters per second. Now, because this is positive also, that means it's going to be towards the pins again. Now, something interesting here is we start with a negative impulse, so we should go slower, and you can see that with the final velocity is less than the initial velocity. Now, something to notice about part A and part B, with the same impulse but in the opposite direction, you get a final velocity that is 0.71 meters per second faster over here, and in this part B we have a final velocity that's 0.71 meters per second slower over here. So because of that positive and negative, that means that we added the velocity in on the first time and then we subtracted the velocity on the second time. Next example, we know this graph from before where we have 1,000 Newton seconds. The 1,000 Newton seconds, that's the total impulse for this graph. So let's suppose we have a 30 kilogram mass undergoes the following impulse, which we already know to be 1,000. Assume that the mass started from 0 meters per second. What's the final velocity? All right, so we start with our equation where impulse is going to be equal to change in momentum. We got the mass is 30 kilograms. We go ahead and plug that in. Final velocity is unknown. We know the initial velocity to be 0. So we kind of clean this up a little bit. We get 1,000 equals 30 times final velocity minus 0. Divide both sides by 30. And that gives us that the final velocity is going to be equal to 33.3 meters per second. The next one, we have these examples right here. If you tried these before to find the impulse, you get the area under this graph right here. For each of those circumstances gives you the impulse. So let's suppose we have a 1.5 kilogram mass that has a velocity of 3.0 meters per second. What's the mass's final velocity for these time intervals? So you can go ahead and try one of those if you'd like. The answer here for 1, 2, 3, 4, 5, 6, 7, and 8, they're given right there. So you can double check to see if you did it correctly with those answers. All right, so we're going to do number 3 together, where we have from 2 seconds to 5 seconds. And if you remember, the total impulse here was 10 Newton seconds. That was the impulse for this part that we did before. So the impulse is going to be equal to mass times final velocity minus mass times initial velocity. Well, the mass is 1.5 kilograms. We can go ahead and plug that in. The initial velocity was 3 meters per second. So we're trying to find the final velocity, and the impulse from this graph is 10 Newton seconds. So we clean this up a little bit. We get 10 is going to be equal to 1.5 times final velocity minus 4.5. We add 4.5 to both sides. Then we divide by 1.5. We get the final velocity is 9.7 meters per second. In this, we have a rocket that has a mass of 57 grams and it's fired from rest. The engine's force versus time graph is given to the right. So what is the final velocity of the rocket after it's fired off? Okay, so this word here, it says integral is going to be 2.641 seconds times newtons. Now that's helpful to give us because if you remember a force versus time graph, the area for a force versus time graph can give us the impulse for that graph. Now there's no clean shape here that we can use in order to find the impulse because we usually turn it into rectangles and triangles, but the computer program actually did it for us and it calls it an integral. Now something to know about an integral is an area under the curve. So it already gives us that number. So we can use that in order to determine the impulse of the graph, and we can use the impulse to find the change in momentum. So we got impulse is going to be equal to mass times final velocity minus initial velocity. Well, it's given in the problem that the mass is 57 grams. That needs to be converted to kilograms, so it's going to be 0.057 kilograms. And it says it starts from rest, so that means the initial velocity is going to be 0. We'll go ahead and plug that in along with the impulse down here, and that gives us 2.641 is going to be equal to 0.057 times final velocity minus 0. All we need to do is just divide both sides by 0.057, and that gives us our final velocity. And we get our final velocity is going to be 46.3 meters per second. In this next problem, it says that Richard strikes a .058 kilogram golf ball with an average force of 272 newtons, and it gives it a velocity of 62.0 meters per second. How long has Richard's club was it in contact with the ball? So we start with our equation. Impulse is going to be equal to change in momentum. Now, in this example, we're given the net force and the time, so we can go ahead and plug that in. 272 times the time, which is actually what we're going to be looking for. And then we got the mass, which is 0.058 times final velocity. The final velocity is 62, and the mass again is 0.058, and the initial velocity is going to be 0 as a golf ball is sitting on a golf tee before it's actually hit. So we plug in our numbers, and since the initial velocity is 0, we'll go ahead and cancel that out. So that's going to be 272 times the time. That's going to be equal to 0.058 times 62. Go ahead and divide both sides by 272 in order to get time by itself, and we get the time is going to be 0.013 seconds. So in this example, we have a 0.145 kilogram baseball that's moving at 35 meters per second when it's caught by a player. Find the change in momentum. Well, change in momentum is going to be equal to mass times final velocity minus initial velocity. Well, we have the mass, that's 0.145. We'll go ahead and plug that in, and we got the initial velocity, which is 35, and it's caught by a player, so it's going to stop. That's the final velocity of 0. So we get 0.145 times a negative 35, which gives us negative 5.08 kilograms meters per second. The second part says if the ball is caught with a mitt held in a stationary position so that the ball stops in 0.050 seconds, what's the average force exerted on the ball? So this is the force that the mitt is exerting on the ball in order to stop it. So we got impulse is going to be equal to change in momentum. We already found the change in momentum. Impulse is going to be equal to net force times time. So net force times time equals change in momentum. We have the time, we have the change in momentum. We're going to go ahead and divide both sides by time. So net force is going to be equal to change in momentum divided by time. So that's negative 5.08 divided by 0.050, which gives us a net force of 101.5 newtons. The last part says if instead the mitt is moving backwards so that the ball takes 0.500 seconds to stop. So this time the person who has the mitt, who's catching the ball, kind of goes with the ball a little bit, so it takes a little bit more time to stop. Now with that, you should realize that if you're taking more time to stop, that means there's less average force that is exerting on the ball. So the question here is, what's the average force exerted on the mitt exerted by the mitt on the ball this time? So we're stopping the ball again, so we got a change in momentum. It's going to be equal to impulse, and we already figured this out. With a change of momentum equal to impulse, and net force times time equals change of momentum. We go ahead and divide both sides. We get the net force is going to be change of momentum divided by time. So that's what we're using here. So we go ahead and take our negative 5.08 and divide by 0.500, and this time we get a net force of 10.15 newtons. Now if you notice something, the time is 10 times the amount of time for the second part. So this was 0.05 while this is just 0.5. So that means it took 10 times the amount of time to stop. With 10 times the time, with more time, you should have less force. So you have 1/10 the force. And if you notice the 101.5 from the second part and the 10.15 newtons from the third part, that is 1/10 of what the force was for the second part. All right, so the next question is, which has more momentum, a supertanker tied to a dock or a falling raindrop. Now, a supertanker has a lot of inertia because it has a lot of mass, but momentum and inertia are not the same thing. Momentum is mass times velocity. So since a supertanker is tied up and has zero velocity, even though it has much more mass than the raindrop, it's only going to have zero momentum. So the raindrop is going to have, even with the tiniest amount of velocity and with the tiniest amount of mass, it's going to have more momentum. The second question is, when you jump from a height to the ground, you let your legs bend at the knees when your feet hit the floor. Explain why you do this in terms of the concepts that we learned. Well, when you bend your knees, what that does is that increases the amount of time that you're in contact with the floor. You increase the amount of time that you are stopping. And by increasing the amount of time, just like in a car wreck, increasing the time decreases the amount of force, so there's less damage done to your body if you bend your knees as opposed to lock your knees as you jump and land on the floor. The next question is, says an archer shoots arrows at a target. Some of the arrows stick into the target while others bounce off. Assume that the masses of the arrows are the same. Which arrows produce a bigger impulse on the target? Well, simply put, this is like the happy and sad bulb. You got the target, the arrows that hit the target and stick into it. That's like the sad ball. They have a momentum and they stop. The arrows that bounce off, the ones that hit and bounce the other direction, they have a greater change in momentum. So they have a greater impulse. So the ones that bounce off are actually going to have a greater impulse. I've actually talked to a cop friend of mine who has talked to some criminals about getting shot by a real bullet as opposed to a rubber bullet. And some of these criminals have said they would rather get shot by a real bullet because a rubber bullet bounces off, which means it has more impulse and it hurts a lot more than the bullet that actually goes through and punctures the skin. Of course, if you hit a vital organ, then all that is moot anyway.